Hi everyone. So in this video we continue with Chapter 6, Modeling Real-Life Phenomena, specifically Section 6.2, Quadratic Models. Quadratic models appear frequently in real-world situations involving area, economics, projectile motion, falling objects, among other things. In this section, we will take a look primarily at quadratic models of the form y equals ax squared plus bx plus c. So a, b, and c here just represent constants or numbers. So an example of a quadratic function would be y equals, say, 2x squared minus 6x plus 1. And then here we could identify a, b, and c. So a in this case is going to be 2, b is going to be minus 6, and c would be 1. Quadratic models are used in situations where the rate of change in the dependent variable changes linearly with respect to the independent variable. For example, falling objects due to gravity, that's called projectile motion. The acceleration is constant, the velocity follows a linear model, and the displacement or position follows a quadratic model. Revenue models, that's the next example. The number of items sold of some item based on the price follows a linear model. The revenue from selling the number of items follows a quadratic model. So quadratic models also have some geometric properties that make them well suited to designing satellite dishes and to modeling bridge spans. Before we begin, we will restate key properties of quadratic functions that you have seen before. Now, one of the important things about the quadratic model is to realize that it has concavity, right? The concavity could be upwards if the number a is positive or greater than 0. So in this case, we have 2. The concavity of this particular function would be upwards, like this one here. Also, it is important to notice that we can find the x-coordinate of the vertex by using this simple formula. X equals minus b over 2 times a. So if we were to find it for this case here, we would say that the x-coordinate of the vertex is going to be x equals minus b, so minus 6 over 2 times a, so 2 times 2. So notice that here we would get 3/2. So that would be the x-coordinate of the vertex and also the axis of symmetry. The axis of symmetry would be this imaginary line that we would draw through that x-coordinate that we just found. And it's called the axis of symmetry because the parabola has a symmetry with respect to that x-coordinate. So this would be the dotted line, and notice that you would have a symmetry to the right and a symmetry to the left. Now, in the case where a is negative, in other words, if we have a negative number here instead of positive 2, then the concavity of the parabola would be downwards. So in the next slide, you're going to find a summary of different characteristics regarding the quadratic function. So for a quadratic function of the form y equals ax squared plus bx plus c, where a does not equal 0, the graph of a quadratic function is roughly U-shaped and is called a parabola. Concavity. The graph of the function is concave up if and only if a is greater than 0. It is concave down if and only if a is less than 0 or negative. Symmetry. The graph of the function is symmetric about the vertical line with equation x equals minus b over 2a. This line is called the axis of symmetry. Maximum and minimum. The function has a maximum when it's concave down or a minimum when concave up, where the graph intersects the axis of symmetry. The point is called the vertex of the parabola. The x-coordinate of the vertex is therefore given by x equals minus b over 2a. The y-intercept of the graph is found at 0, c. The x-intercepts of the graph, also called zeros of the function, can be found with the quadratic formula, which is minus b plus minus square root of b squared minus 4ac over 2a. Remember that a graph may have 0, 1, or 2 x-intercepts. So now let's take a look at example 6.5. And it says, a ball is thrown upwards from the top of a building. The height of the ball from ground level can be modeled by the function h of t is equal to minus 4.9 t squared plus 11t plus 50, where h of t is the height of the ball in meters and t is the time in seconds after the ball was thrown. Part A, sketch a graph of the function. So notice that the value here for A is minus 4.9. So because this is negative, it means that the function has a downward concavity. We also know that C, 0 comma C, is the y-intercept, or in this case, the h-intercept. So we could start by sketching a graph. And first of all, we say that this is t for time in seconds. So time in seconds. And then this would be the height in meters. And then we know that it starts at a height of 50, and then it goes up and back down. We still don't know when it reaches the ground, but that's one of the questions we will have to answer. So it says for B, write down the height of the building. So the height of the building, as we said, is 50 meters, because that's the starting point. Find the time when the ball reaches its maximum height. So for that, we use the formula t equals minus b over 2a. So that means it's going to be minus 11 over 2 times negative 4.9. And this is going to give us approximately 1.12 seconds rounded to 3 significant figures. For D, find the maximum height. So the maximum height is going to be at time 1.12 seconds. So we plug that time into the function. So we need to find h of 1.12. So that's going to be minus 4.9 times 1.12 squared plus 11 times 1.12 plus 50. Plug this into the calculator, and you're going to get approximately 56.2 meters rounded to 3 significant figures. For E, they want us to find the time when the ball hits the ground. So that means when the height is equal to 0. So they want us to find this right here, this point. In other words, the x-intercept, or the t-intercept in this case. So for this, we use the quadratic formula. Remember that it's t equals minus b plus minus square root of b squared minus 4ac over 2a. So all we have to do is plug in the constants here for a, b, and c. So b is 11, so that means that we have to write minus 11 plus minus square root of b squared, so 11 squared, minus 4 times a, which is negative 4.9, times c, which is 50. And all of this over 2 times a, or 2 times negative 4.9. Now, why plus minus? Because normally these have two solutions. In this case, we're going to keep only the positive solution because obviously this problem is a problem of time, and time is not counted in negative terms. So let's forget about the minus here, and we'll focus only on the plus solution. And we plug all this into the calculator. It's going to give us 4.51 seconds rounded to 3 significant figures. So this would be when the ball hits the ground. So that means that this point here is 4.51 seconds. Now for F, describe a reasonable domain and range for this model. Now the domain would obviously be between 0, so the domain would be the time. And notice that the time starts at 0, and the ball hits the ground at 4.51. So that would be a reasonable domain for the time. And the range, which is the height, would be from 0, which is the ground. So the height, the maximum height, would be 56.2 meters. So that would be the reasonable range. So now I'm going to show you how to use the GDC to solve the same problem. So first of all, let's sketch the graph using the calculator. We go to y equals, and there we plug in the function, but this time in terms of x. So minus 4.9 times x squared plus 11x plus 50. Now, before we hit graph, we want to make sure we have an appropriate window. So the minimum for x could be 0, and let's make it 10 seconds for the time as a maximum. The minimum height would be 0, and the maximum height would be above 50 meters, let's say 60. So now we can hit graph. And there's our function. Write down the height of the building. Well, we already know that that's 50. So for C, find the time when the ball reaches its maximum height. For that, we can use the calculate function. So second, calculate, and we want to use number 4 that says maximum. Then it'll say left bound, so make sure you have the cursor to the left of what you think is a maximum height. So notice that we're to the right, so we need to switch to the left-hand side of where we think the height is, the maximum. There we go, so hit enter, and then right bound, move the cursor to the right of what we think is a maximum, hit enter again, and then it's going to say guess, hit enter, and there it is. So notice that the maximum is also at 1.12. So we write 1.12 seconds rounded to 3 significant figures because that's when the ball reaches the maximum height. Find the maximum height for D. We already have it. It's right here, 56.2 meters. Rounded to 3 significant figures, right? 56.17, which we round to 56.2. Find the time when the ball hits the ground. For that, we can use the calculator again. For this, we use a function, which is 0, number 2. So click on that, and it's going to say left bound. So left bound would be a little bit above the x-intercept. So let's hit enter there. And then we go down and hit enter again, and there is our x-intercept. So notice that it says x equals 4.508, so 4.51. So that would be 4.51 seconds. Notice that y says equals 0. So that's when it hits the ground. And then the reasonable domain and range, for the time it would be between 0 and 4.51 seconds, and for the height it would be between 0 and 56.2 meters. So we continue with example 6.6. And it says, the number of jeans sold by a clothing store can be modeled by the function n equals 1000 minus 5 times p, where n is the number of items sold and p is the price of the jeans in euros. Part A, develop a model for the revenue earned from selling these jeans based on the selling price p. So in general, we have that revenue is equal to price times the number of items sold. So in this case, we could say that R for revenue is equal to P, price, times 1000 minus 5P. So if we multiply and expand this, we're going to get that the revenue is equal to, I'm going to rearrange it, minus 5P squared plus 1000P. So this would model the revenue, and it's a quadratic model, obviously. So for part B, it says, use your model to find the price the jeans should be sold in order to maximize revenue. So that means finding the vertex of the parabola. Now this one is downward, has downward concavity. We can see that because A is -5. So we can use the formula minus B over 2A. So in this case, minus 1000 over 2 times -5, and we are going to get 100 euros. So this would be the price for the jeans that would maximize revenue. C, find the maximum revenue predicted by your model. So that is simply going to be plugging in the 100 into the equation. So R is equal to minus 5 times 100 squared plus 1,000 times 100. And here we're going to get 50,000 euros. So this would be the maximum revenue predicted by the model. For D, they want us to give a reasonable domain and range. So the domain, let's think of the domain in this sense. If you have a downward parabola, let's suppose that we have a graph and this parabola looks like this, the reasonable domain would be between these 2 points, between the p-intercepts in this case, right? So what we need to do is equal our function or our model to 0, and in order to find what this value is and this other value is. So if we have minus 5p squared plus 1000 p equals 0. So to solve this, we could use the quadratic formula, but that's too complicated, and it's much easier here just to factor. So notice that I could rewrite this expression as minus 5p times p minus 200. Notice that if I multiply this times this expression, I'm going to get this again. So this is the factorization of this expression. And notice that here we would have two solutions. P could equal 0 or P could equal 200. So these are the p-intercepts. That means that the graph actually goes through here, through 0, right? And here it would be 200. So that means that a reasonable domain for this case would be for P to be between 0 and 200 euros. Whereas the range is going to be between 0 and the maximum for the revenue, which we found was 50,000. So next we have example 6.7, and it says the Sydney Harbor Bridge is supported by two spans that can be modeled by quadratic functions. The lower span is approximately 503 meters wide and 118 meters tall at its highest point. Develop a quadratic model, so they want a quadratic model for the lower span, such that one end of the span is positioned at 0, 0. So this is what the situation would be. So this is the lower span right here, and as you can see, it has a sort of U shape. So we can use a quadratic function to model this span. And notice that the one end is at 0, 0, which would be right here. And the other end would be at 503, 0. Why 503? Because that is the width of the lower span. And then we would also have a point at 251.5 for x. Why that? Well, that's exactly half of 503, and we know that these quadratic functions are symmetric. So the midpoint would be the maximum in this case, and the maximum height is 118 meters. So they want us to develop a quadratic model. So quadratic models are in the form y equals ax squared plus bx plus c. Now in this case, c is always a y-intercept. So in this case, it's 0 because we have the point 0, 0 as the starting point of this parabola. So we can say that c is equal to 0. Therefore, we can simplify this function as y equals ax squared plus bx. So we need to find a and b. For that, we're going to use 2 points. We know that we have the point 251.5, 118, and we also have the point 503, 0. So that means that we could set up two equations and solve a system of equations. What do I mean by that? Well, notice that 118 has to equal A times 251.5 squared plus B times 251.5. And then we also know that 0 has to equal A times 503 squared plus B times 503. So let's expand this and rearrange it. So I'm going to do that over here to the left. So we would get two expressions. One would be 63,252.25a plus 251.5b. And this equals 118. And then we would get another expression, which would be 253,009a plus 503b equals 0. So this here is a system of equations. Now, it's very difficult to solve this manually. And in the GDC, under Apps, you have a button that says Apps, and from there, you go to the polynomial solver. Now, my emulator does not have this application, but I'm going to be giving you guys a link to a video that will show you how to do it with this particular app. But what I will show you with my calculator or my emulator is how to do a quadratic regression using points. So I'm going to show you how to do a quadratic regression. I'm going to write that here, quadratic regression. So we have 3 points that we know of. We have 0, 0. Then we also have the point 251.5, 118. And we also have the point 503, 0. So in the calculator, we want to go to Stats and Edit, and you're going to find lists. So notice that it says list 1, list 2, list 3, and so forth. So in list 1, what you're going to do is write the x coordinates. So 0 is one x coordinate, 251.5 is another coordinate for x, and we also have a third coordinate, which is 503. And then in list 2, we're going to write the corresponding y coordinate. So 0, 0, 251.5, 118, and finally 503, 0. So once we do that, we go to where it says stats again and calculate. And number 5 says quadratic regression. So you click on that, hit enter, and it takes you to the main screen and it says quad reg. Now normally you guys are going to have options for the lists, but if you don't have them, you have to do it manually. So you're going to do this. You're going to type parenthesis, and you're going to go second 1. That's list 1. So list 1 is your x coordinates. That's what you're telling the calculator. Comma, second and 2 will give you list 2 for the y coordinates. So now all you have to do is hit enter, and the calculator is going to give you the quadratic model. So notice that it says y equals ax squared plus bx plus c, but then it tells you what a and b are. You see that a and b are on the screen. So that means that we already have the model ready. So notice that the function that would model this situation would be y equals minus, because this is a, minus 0, 0.001866, let's round it to that, x squared plus b, which is 0.9384 times x. Now c is 0, as we had found before. So this function would model the lower span of the bridge.